today I'm going to be talking about what a design problem actually looks like in MapleSim. So we're going to be going through and just kind of showing you what that workflow actually looks like, because I find it is really different from other tools. So the design example I've chosen for today is the feedback linearization of a robot. So it's a control design example. And so just a little bit about where MapleSoft comes from as a company to start. So we really have a strong background in mathematics, and that's where our original Maple product was developed. And it's a symbolic mathematics engine. So it gives you all kinds of tools for working with equations, doing analysis, and it's been a very good thing for us to build from when going into the engineering world. So we started moving into engineering problems because they're all math problems with some context, essentially. And so this is where MapleSim came from. It's our simulation analysis package for working with dynamic systems. And we also have our applications engineering group here that does contract-based engineering system solutions using MapleSim and our other products. And so this has really changed how we look at some of the problems that we're dealing with. And it changes the solutions that you get from your analyses. So really, when you look at engineering, you're always working with equations. And that's the natural language of the engineering problems. Whenever you break open a textbook, there are always equations staring you in the face. So there's lots of equations, and there's usually no code to tell you how to implement those. So the odd occasional textbook might include something like that, but it has equations just describing the physics of your problem, and the actual implementation is up to you. And so this is something that's going to come out here when we look at our path following example that I'm going to be presenting. So we're going to be using these equations and building up a model here. We're going to build up a controller based on the model that we have. So the application that I've chosen here is engraving. So if you have a robot arm and it's going to be cutting a path onto a surface, and it's going to be making that mark using an engraving tool. And so really you have two objectives. You want to move that cutter to your desired path, and you want to move it along the path at a certain speed. So if you go too fast, it might produce a rough edge, and if you move too slow, you're wasting time. So this is where it's going to get a bit more into equations with control design theory, but if you're not familiar with control design theory, that's okay, because the main point today is the equations that you see here just get put directly into Maple later, and we can just work right in this natural formulation of the problem. So first off, we have a nonlinear state space system. And so they have this form where you have some dynamic equations and you have an output equation. So usually the dynamics would tell you how the joints are moving in a robot for a given input U here, which would be the torques on the joints. And then Y is the output, which would be the position of the end effector. So it's where that engraving tool is located in 3D space. So today what I'm going to look at is you can introduce a new set of task coordinates, and we'll call those guys Z. And this represents a circle that I want to engrave at a specific location in space. So there's two components here. And the first one, the first group of two equations, they form a circle in 3D space. So that tells me where I want the end effector to be. And then the last one is actually the arctan here. That's going to be an angle that tells you where you are on the circle. And we use these task coordinates to form a virtual output. So you can express what your virtual output is with respect to the state vector. And so this sigma function becomes really important for the problem. So with this sigma, with this z function defined, when these two components of your task coordinates are 0, you're on the circle that you want to be on. So we want to drive those things to 0. With the arctan, with the angle along the circle, that angle is something that we want to have a constant velocity, so that that tool will move along the circle at a constant speed. And so this is what you'd see from a control design paper for the formulation of the problem. And then next, it would be a question of what do you do with those equations? How do you get the robot to do what you want it to do? So there's a little bit of notation here. The lead derivative is written as LF of sigma, and that's just the partial derivative of sigma with respect to x times the vector f. So you're multiplying a partial derivative by a vector field. So if you take the virtual output and you differentiate it once, you end up with an expression that looks like this. So you can write out what the derivative of z is using these Lie derivatives. Because it's a mechanical system that has a certain form, and it's a second order system, the first term here goes to 0. And so that's something that's a result from literature, and I've got a link to the paper on the next slide. But yeah, if you're not familiar with control design, don't worry about it. For those of you that do know about it, it says that the relative degree of this system is not 1, it's higher than 1. So which makes sense because mechanical systems are second order systems. So if you differentiate that z vector again, you can write the dynamics of the system in this form. And the control input u now enters into the equation. And that's a really important part because that's the u that we're going to be choosing to get the robot to do what we want it to do. So this is where feedback linearization comes in. So we can choose our controller in this way, and that'll do something very special for us. So this is the z dot from the last slide, and with this u, what you're doing is you're canceling out this matrix here in front of the u, and then you're subtracting away this term with the LF2 of sigma, and you're adding in a new inner control loop variable. So what this does is essentially subtracts away the dynamics of the robot and then adds in the dynamics that we want it to have. And so you have this very simple closed loop system that says that the z double dot is going to be equal to v, and we can choose v to be whatever we want it to be. So that's how you actually get your desired dynamics implemented in the system. And there's the paper that I was talking about before. So from here, we're going to jump out and we're going to go into MapleSim. And so in MapleSim, what we have is a very simple looking model, but we'll drill down into the blocks. So we have a controller here that I've designed, and we're going to go into the worksheet for how I designed that. But first, I just wanted to show you that inside this block, there's a model for the robot that we're going to be analyzing. So this is a Kuka robot, and what we've done is we have 3 revolute joints in here that are connecting up the different links of the robot. And temporarily, for this example, I've locked down the other 2 joints. So I've taken out the revolute joints and I've just replaced them with rigid links, so that we're only considering a 3 degree of freedom example today. And then it's going to be this robot whose equations that we end up extracting from the worksheet. So there's some torque drivers here that serve as inputs to my system, and then angle sensors that serve as the outputs to my system. And so this is the system that I want to analyze, the equations that I want to gather and work with. So to do that, in the attachments for the model, we have this worksheet called feedback controller. And in the feedback controller, I'll just go to the top of the sheet. And that's taking a second. So in the feedback controller worksheet here, you have programmatic access to the model that's sitting in your MapleSim diagram there. And so what you can do, I would do this live if the computer were a bit faster, because it really doesn't take that long on a reasonable machine. But you have the MapleSim link model command actually gets you a programmatic handle to the model. And then I can look at the subsystem that I'm interested in this case, the robot. You can choose some nice name substitutions to make things more understandable or shorter so that it's easier to look at. But in this case, I've chosen them so that it corresponds to common conventions in robotics. So Q are the names of your joint angles. So I've said that the revolute joint 1, its angle is going to be Q1. For the second revolute joint is Q2, etc. And then the moments about the joints are going to be my control inputs, my U1, my U2, my U3. And then when you call this get multibody command, what it's doing is it's analyzing the system. It's figuring out what a good set of coordinates are for your robot and forming the dynamic equations of the system. So what we have here is a system without constraints. So we have a constraint-free system, and that's why you see zero algebraic constraints. If you have a manipulator that has a kinematic loop in it somewhere, then you're going to have something of a slightly different form than what we're seeing today. But you can still do this kind of analysis. It just becomes a little bit more complicated. There's a lot of housekeeping in this section for variable names and substitutions, but what I want to focus on is this is the internal representation that multi-body command has built up for your system. So in the constraint-free case, what we have is a mass matrix, xm, times the acceleration of the joints is equal to some force vector. And we can reform that into that nonlinear state space form. So we have, this would be our x dot vector. It's going to be formed of q dot, q double dot. Our f vector is going to be the joint velocities, and then the inverse of that mass matrix times vf minus u. So in this case, we're lucky that vf is affine in u. I guess not lucky so much as it's by construction. When you have a robot of this form and you have torques that you're applying directly to the joints, your inputs are going to be, you can separate them out as a vector. And then the g vector has that inverse of the mass matrix as well. And one of the neat things is that you can just take this multi-bodied mass matrix, and it looks horrible and complicated, but when you're looking at it, when you see these fractions that have large numerators and denominators, the reason for that is that there's an exact representation of the model here. We're not doing math in floating point coefficients that would lead to possible losses of accuracy as you're manipulating expressions and you're losing digits here and there as you do different operations. So this is being represented exactly so that you could look at this as a floating point number with arbitrary precision. And then the rest of the matrix here is written out in terms of cosines and sines of joint angles. So it's something that you'd expect from a robotics textbook. But if you've worked much with those matrices, you know that it's really hard to find examples that are simple enough that you can still write out these matrices by hand. And that's where I love tools like Maple and MapleSim, because these expressions are getting big, they're getting huge, but I don't ever have to work with them by hand, so it's completely fine to have a large mass matrix. And if we keep scrolling down, you see it just keeps going for a while. Computationally speaking, though, you have a lot of the same terms in here. There's a lot of cosines, there's a lot of sines. So when you go to calculate this matrix, it's not actually that expensive. So it looks complicated, but there's so much structure in here that you can find smart ways to calculate it. And that's exactly what MapleSim is doing behind the scenes. And here's where we get into the part where it's more directly connected to the mathematics that you get from, say, an academic paper or an engineering textbook than a lot of other tools that I've worked with. So we can invert that mass matrix by just using linear algebra matrix inverse. And so this gets us a full symbolic inverse of that matrix. And I'm not going to print too many more expressions here because they start getting very, very large. And some of them, the controller at the end would likely take several pages if you ever tried to print it out. But they're completely within the scope of Maple and MapleSim to work with. So the bottom part of that f vector we can form by taking that inverse and multiplying it by the difference of the vectors for the forcing vector and the inputs. So you can build up your f and g vectors from that nonlinear system representation. Your forward kinematics are also something that's very easy to get. So this is that relationship that gives you the output equals h of x, that y equals h of x. And from that multibody object, you can use the get frame motion command. And so what we're doing is we're just asking for the relative translation of this frame relative to ground. And so this is, you can see from the naming convention, the main is the top level of the model. So we're looking at the robot's fifth link, and F2 is the frame, the second frame, which is where the end effectors tool would be. And we can express those forward kinematics with respect to the state variable. And so you get these equations that are, again, giving you what your output equations are. The virtual output we can define. So I've got an expression here that's the circle. So really in 3 dimensions, this is a cylinder intersected with a plane, so that gives you a circle. And then we have that arctan, that angle on the circle for our position coordinate. So we can define those naturally in Maple. And then what you can do is you can say, I want to form that sigma function by substituting the forward kinematics into my task coordinates. So you're doing this evaluation, and again, you end up with something that's complicated, but it's an exact representation of the model's behavior and an exact representation of what your outputs should be. So there's no approximations here, and you get something that's easy to work with within Maple and easy to analyze. So for the next step, we're going to form the inner loop controller. So if you remember, the outer loop, the feedback linearizing controller, gives us this relationship that z double dot is equal to v. And here I find it easier to start from the bottom and work up. So for v, we have that we're going to have a proportional gain times the z vector minus the derivative gain times the z dot vector. And here we're doing a difference because we have a desired velocity in the third coordinate of the task coordinates. So this is saying that we want the derivative of that arctan to be equal to 1. And that would give us a velocity of 1 radian per second around that circle. And so we can define what the proportional and derivative gains would be. And you could make these parameters for the system, but I was just putting together a simple example here, and so I've put them in as constants, but you could make them as parameters for the blocks that you see in the MapleSim diagram. To formulate the outer loop controller, if you remember, we had the expression from the slides that looked like that, and we can form these Lie derivatives by actually just differentiating what the virtual output was. So those coordinates in task space as expressed with respect to the state variable. And so what I'm doing is I'm taking a Lie derivative with respect to those x variables and multiplying by f, etc., etc. So you can form your LF sigma, your LG sigma, and if you remember, I said on the slides that goes to 0, and you can verify here that it does go to 0, and you'll see that it's exactly 0. So it's not that if you're doing some computations numerically, maybe you get a matrix here that has small entries, and you're left with the question of, does this really mean it's 0, or does it mean that there is some numeric error somewhere that I didn't pick up, there's some uncertainty when dealing with the numerical computation sides about what small values actually mean. But here with the symbolic manipulations, we see that it's exactly 0. And so you know that this really is a system that has a relative degree greater than 1. Okay, so you can form out the other Lie derivatives. And there's a little trick you have to use to minimize Maple's computation work when inverting a matrix with large symbolic entries, but that's documented in the help page. And so you can form the inverse of that LG-LF matrix. So when it comes down to writing out the controller, that is exactly the expression that we had originally for the controller that we wanted to find. So if you look up here and compare the two, it's a very natural way to implement a controller. There's some name substitutions I have to do, but that's really more accounting than anything else here. So once you have this expression, we have these giant equations here that describe what our inputs are. We can go and create a Modelica component from them. So I just want to point out a few things here. So we have this Maple to Modelica command that can take the equations for the controller, and it's going to generate a component. And so that component was that block that I pointed out on the MapleSim model at the top level. And so it's going to be a type named feedback controller. And we can define that the inputs are the joint variables and the outputs are the control outputs. And when you use the set component command, this is going to take that Modelica component and attach it back to your MapleSim model. So if we go back into the MapleSim model, you'll see that under the custom components listed here, there's now a feedback controller component. So this is that Modelica that I've just attached to our model. And if we go back to the top level of our system here, you can see that this component that I've added is that feedback controller. So every time you regenerate that component, this little custom component here will be refreshed. So if you run the simulation, which I've done already, you get this 3D visualization that you can actually see an animation of your results. So in our case, we're going to see that robot track onto that circle and start doing its engraving task as it goes around and around. So you can see that the robot drops down quickly towards a circular type path and then kind of more slowly approaches that circle until it finally gets there. And now it's moving around at a constant speed, which is exactly what we wanted. One of the benefits of the feedback linearization controller that we used here is that, unlike the PID controllers, there are terms in here that account for the centripetal acceleration needed to stay on that circle. The PID controllers, like I was saying before, they're a linear controller, and so they don't handle these nonlinear constraints perfectly. So what's happening if you use a PID controller instead is that you're actually going to drift outside of this circle, and you're not going to track the circle perfectly. You can add additional terms to PID type controllers to try and compensate for that, but then you're already into a nonlinear control design and you may as well use a more sophisticated technique. So with the results that we've generated here, you've got a nice animation that shows you exactly what your model is doing, so it provides very intuitive results. And it's taken in CAD geometry here to show what the actual robot will look like. And if we head back into the MapleSim model, one of the things that I really like about this is that the individual links in here actually come from CAD diagrams. So if you look here, there's STL files that have been attached to this model. It's pulling in that 3D geometry from those CAD files, and it's also pulling in information about their inertia, center of mass, and mass. You just have to insert what the mass density is, so whether the robot's made of steel or aluminum or what have you. And if you've ever tried working with robots then and coming up with their dynamic equations, it can be very difficult, even for a simple robot, to determine its inertia and center of mass by hand. So being able to automatically import it from other tools is a great advantage, and it really helps your simulations come to life. So that's all we have for our presentation here today, and I'd like to thank you for joining me here. I'd just like to remind you that we have plenty of other resources on our website. There are tons of models that we've made available through the MapleSim Model Gallery to help people see how you can approach different design problems. So these are models with analysis worksheets attached from all kinds of different disciplines in engineering. So there's something there for everyone. We have other recorded webinars on our website. We have our online help pages that show you what the commands are that we offer and what they do. And so there's lots of resources, and I encourage you to explore our website. It's a great way to get lost for an afternoon.